Right, welcome to London Learning Lean. Next week, we have Alex Best, who's going to talk about solving Diophantine equations via the class group. But this week, very pleased to welcome Oliver Nash, postdoc here at Imperial, who's going to tell us about ergodicity and Gallagher's theorem. Over to you, Oliver.
Thanks, Kevin. Yeah, it's actually good to hear that Alex is talking about solving Diophantine equations next week, because I'm talking about approximating them this week. But he's going one step better. Yeah, okay, so I'm going to talk about ergodicity and Gallagher's theorem. So Gallagher's theorem is a result that I only learned about a few months ago from Andy Pollington, who said it might be a nice formalisation target. And I thought it was a really nice experience and a good example of kind of sorts of things that are now quite easy using MATLib and Lean. So this is really just usual sort of advertisement for MATLib and demonstration that we can do modern mathematics, and an example of something that I myself thought was quite nice. Okay, so let me first of all tell you the relevant background. So here are three theorems that kind of frame the ideas that I want to talk about today. So the first one's very old, 180 years ago. Probably most, if not everybody, has heard of it. So this is Dirichlet's theorem, and it says that if you're trying to approximate real numbers by rational numbers, and then you want to do it sort of quadratically well with respect to the denominator, then you can do this exactly when the number is irrational. So the condition here, so you know the mod of x minus q is less than 1 over the denominator of q squared. But the key thing to notice is this IO hiding there. So this is infinitely often. What that means, you know, this statement actually means there's an infinite sequence. So given x, there's an infinite sequence of rationals q, so q1, q2, q3, and each of them satisfies this condition: x minus q is less than 1 over the denominator of q squared. So this this set of real numbers came up in the course of Dirichlet's work in algebraic number theory, and he needed to characterize it, and he discovered that actually this set I is actually exactly the irrational numbers. And there's a small bit of work there. So this is this old theorem of Dirichlet, which is a useful theorem. Then about 100, I mean, a lot happened, but about 120 years later, there was this theorem due to Gallagher, part of his PhD thesis, I think, and so there's lots of ways to reach these results have been generalized, but it's this one sense in which you can generalize it, which is to say, okay, instead of just focusing on an approximation within this sequence of 1 over the denominator squared, let's continue to index by the denominator of the rational number, but let's just let it be any sequence of real numbers that determine the quality of your approximation. So we consider, you know, real numbers such that there are infinitely many, so infinitely often I can approximate that real with a rational number, and then the error term is controlled by this input, this sequence, delta I. And so, you know, delta I is 1 over I squared in the case of Dirichlet's result. But Gallagher allows any old delta I. So, and then Gallagher's theorems, this is mostly what I'm going to talk about today. It says there's this kind of amazing all or nothing property. So it says that, okay, the real numbers, you know, given any sequence of reals, then those numbers which can be approximated infinitely often, it's either, you know, almost no numbers, this almost everywhere is what I mean by this AE. So this is the measure theorist's concept of equal up to sets of measure zero. So it's either almost no numbers or it's almost all numbers. And, you know, as a consistency check to do immediately, Dirichlet has a specific example of this. You know, is this almost all or almost no? Yes, okay, the rationals of measure zero. So indeed, this is almost all numbers in Dirichlet's case. Okay, so then as soon as you have Gallagher's theorem, you know, you might say, okay, fine, given a sequence of reals, which are my error terms, like maybe it's 1 over I squared as like Dirichlet had, or maybe it's some other sequence, I know that it's almost all numbers or almost no numbers, but, you know, which is it? And just a few years ago, there was a breakthrough. So Kougalopulos and Maynard, they proved a theorem which gives the exact characterization. I said, okay, yeah, if you give a sequence of delta n's, then, and you want to know whether or not you can approximate almost all or almost no numbers relative to delta n infinitely often, then all you need to do is you sum it against the totient function. So phi here is Euler's totient function. And if it's finite, it's almost no numbers. And if it's infinite, then it's almost all numbers. So these are the three theorems, 3 bits of history. A lot, I've excluded a huge amount of history, and it looks a bit random. Like, why would you even study these 3 things? I might say a little bit about, why we should care about these results, but as I go, yeah, these are kind of the main kind of waypoints. And I'll say a little bit about each, and I'll say most of the time we'll be talking about Gallagher's theorem. Okay, so first of all, the theorem that I understand the least, and that's the biggest, the best theorem, so the Cuckolopoulos-Maynard theorem. So this is worth highlighting, and this was the reason that I worked on Gallaghers theorem at all, was this recent theorem from 2019. So it tells you 2 things. It tells you that if this particular sum converges, then the set of approximations is almost empty. So that's actually easy. That's just a corollary of the very old Borel-Cantelli lemma, in probability theory. If you don't, it doesn't matter, but it's an easy elementary result, like an undergraduate could prove this. Then the other thing it tells you is that if the sum diverges, this should say, this, of course, I have a typo here. This should say this is R. So we should have sigma equals infinity implies W is almost equal to R. This is super hard. This was conjectured actually before Gallagher even proved his theorem, conjectured in 1941. And it was regarded, according to the sources that I read, it was regarded as one of the most important open problems in metric number theory for about 80 years. Maynard, of course, got a Fields Medal last July. And his proof of, Maynard did tons of stuff, right? He does these amazing results in prime gaps and all sorts of things. But even in spite of all that work, they highlighted this theorem with Cuckolopoulos that he proved if this thing diverges, then you have almost all numbers. So they mentioned this in his Fields Medal citation. So, serious people think this is a worthy result. And so, yeah, so then somebody mentioned this to me, Andy Pollington. And so then I looked at the result, and I could see that, the question you ask yourself is like, could we formalize this in MathLib? Because it's, just like learning normal mathematics, when you're teaching mathematics to yourself or to another human, how do you decide what to learn? Because it's almost an infinite amount of stuff. Well, recent important results, figuring out how to understand those, that's a good means of educating yourself. And likewise, it's a good means of educating the computer. You say, okay, could I teach the computer Maynard's and Cuckolopoulos' proof? And the answer is, I think, yes, you could. But, there's some groundwork to do. And one of them was Gallagher's theorem. So I said, okay, fine, I'll have a go at that. Right. So that's all I'm going to say about that theorem. I'm still reading it and understanding it myself. I think it's a really nice paper. Obviously, I recommend you have a look as well. Okay, so I mentioned 3 theorems. That's the most advanced fun theorem. There's already this old result. I wanted to just briefly say a few words about Dirichley's theorem as well. So, okay, so I've just repeated it there for convenience, so we have it again. So first of all, totally independently of me, nothing that I was doing, but in parallel with my work in Gallagher's theorem, actually 2 people, so Michael Stoll and I think Michael Geisler, I think is a student of his, they formalized Dirichley's theorem. So okay, so it's an elementary proof, but it's still a bit of work, and not only did they formalize it, but they actually wrote it to a really nice standard, and it's in MathLib and it's available. So that's one reason I want to mention it. And the other reason is just give a little bit of motivation for, I've pulled 3 theorems out of the literature here, and I said, let's talk about these, but why should we? Well, a lot of people will know, why you should care about Dirichley's theorem, but just in case you don't, there's something called Pell's equation. Pell's equation looks like this. So you try and solve x squared minus dy squared equals to 1. For integers x and y, and where d is square free, because d is an integer, and if it's a square, well, the equation is trivial. So if d is square free, and why do you want to solve that? Well, why did Dirichley want to solve that? Because he did. Well, this is because you're looking at the quadratic field extension, q square root of d. It's not terribly legible. And you're interested in the algebraic integers inside that, and then you want to find the units of that. And then if you want to do that, then it turns out you need to solve this Pell's equation. And how do you solve Pell's equation? Well, you start by factorizing it. x minus y root d, x plus y root d equals 1. And then if you have this, then if you have a good approximation, let's make this a bit clearer. I'm being a bit too sloppy. If x and y are a good approximation to the square root of d, then you can make progress. And if d is not a perfect square, which is the interesting case, well, then square root of d is irrational. So you need the fact that, you know, root d is irrational, and so therefore there's infinitely many solutions to this rational approximation and so on. So I'm deliberately kind of skipping over pretty much all the details there, but all I really want to say is, you know, there's an actual question. The units of the integers in a quadratic number field is definitely an important thing to know about. And one approach to understanding that is via the solution of Pendel's equation, which can be solved by means of Dirichley's approximation result. And Gallagher's theorem, you know, is one generalization of that, which is actually interesting for its own reasons as well. So, okay, so just more background. And yeah, of course, it's, you know, it's theorem of number theory. Okay, so then finally, we better get to Gallaghers theorem, which is what I really want to talk about. So again, I'll repeat the statement. So see that I have any typos now, I've got this right. So you have a sequence of real numbers. We're looking at those reals which are have infinitely many good rational approximations relative to this sequence of real numbers in the sense described by the equation. And then we want to prove this all or nothing result. So you know, almost all numbers or almost no numbers. So I worked on this on and off, like in parallel with some other work for a few months last year, and added it to MATLib, or added most of it to MATLib. Yeah, so it's true with a hypothesis that can be removed, but it's an independent piece of work. So so far I haven't said too much concrete about lean itself, but here's some lean code. So it's, you know, I quite like to put, when I can, the informal mathematics and the formal mathematics side by side, just so you can compare. And so here we see like the formal statement of the result of Gallagher's theorem that exists in MATLib. This is the direct copy and paste from MATLib's. I think I've truncated the name to make it fit on the slide. So this says, you know, delta, we have a sequence. Now I've got this hypothesis. This is why I say it's most of. So actually there's two branches to the proof of Gallagher's theorem. It's kind of amazing proof to me because first of all, you assume that you've got this sequence converging to zero, and then you do this long measure theoretic argument that I've formalized. And then you get the conclusion that you want. And then you say, okay, but what if my sequence doesn't converge to zero? Well, you assume the opposite. And then you do a non-measure theoretic number theory argument, and you get the same conclusion. And then you say, okay, well, if I exclude the middle, it's true unconditionally. So the hard bit is actually what I formalized, and the other bit's not trivial, but it's relatively easier. So anyway, that's all just to say the hypothesis here, H delta, that can be dropped. And if it weren't for the MATLib 4 port, I'd probably have done it, but I don't want to keep adding to MATLib 3. I already said Dirichley's theorem corresponds to delta m being 1 over n squared. So this is, in a sense, it's a generalization. And it's a measure theoretic. So, you know, how do you prove a result like this? Well, hopefully I'll give you a sense, you know, by the end of the talk, but it depends on ergodicity, which you may or may not know. And, you know, it's ergodicity of what will have maps on the circle. So you need to pass to the circle to get this result. And then finally, it's a theorem of metric number theory. So yeah, just to highlight, and this is why I was saying Dirichley's theorem is a theorem of number theory, but Gallaghers theorem is a theorem of metric number theory. So, you know, metric number theory, what is it? Well, it's obviously, you know, no field of mathematics has a precise definition, but to the extent that it has a definition, I would say it's the study of arithmetic properties of the reals, let's say, in related spaces that hold up to sets of measure zero. So a number theorist, thanks to Dirichley, says, oh yeah, well, numbers with quadratically good rational approximations, that's exactly the irrationals. But a metric number theorist says, look, I don't care that it's the irrationals, I just care that it's almost all real numbers. So that's kind of the difference. And you know, why would you settle for this weaker answer? Well, you can answer more things at this level of detail. So if you're only interested up to sets of measure zero, more questions of answers. And also, like if an example being Gallaghers theorem. But if you consider Gallaghers theorem, you consider your input as a sequence of distances. One, it's 1 over n squared, maybe, or maybe it's some other decaying function, hopefully. If you want to be able to characterize, like the Cuckolopoulos and Maynard theorem, you want to be able to characterize the solutions, you probably should only care up to sets of dimensions 0, because otherwise, like little small variations you could pick on any given number that has an infinite sequence of rationals approximating it. You could tweak your distances to just pick on that number and get it inside or outside the set. So it's reasonable that you should be interested up to sets of dimensions 0. Okay, so that's like a little bit about a big theorem that's a recent breakthrough, a little bit about the background to Dirichlet, a little bit about Gallagher's theorem and metric number theory. And then I just thought I'd go through kind of how you actually prove this and how I proved it in Lean and what that meant for the MATLAB library. So okay, so I said you need to pass to the circle. So this is like a totally straightforward but important thing to do. So so we've got this set W, and this is like the primary object of concern in Gallagher's theorem. It's those real numbers with these rational approximations relative to the input sequence delta. So it's obviously translation invariant. So let's just get some fresh space. So if Q is an approximation to X, well 1 plus Q is an approximation to 1 plus X, and it has the same denominator, right? So the denominator of 1 plus Q is the same as the denominator of Q. So so 1 plus W is W. So so we're really working in the circle R mod Z. And then when you pass to the circle, how much of the definition of this set W, how much of it can we say intrinsically just in the language of the circle itself? Well, the rationals, those are just the points of finite order, and the rationals with a given denominator in those terms, these are the points of order n. So okay, so we'll stop talking about rationals and we'll just start talking about points of order n. And then the next thing, we need a notion of distance. We need to be able to talk about x minus q, or when we're down in the circle. But yeah, the circle's a normed group. Prior to working on this, I was a tiny bit surprised I'd never copped onto this before. But yeah, the circle has a natural norm. So if you have an element of the circle, one way of thinking about the norm is you pick a real number which is a representative, you round that to the nearest integer, and then the distance of that real to where you ended up. That's the norm of an element, and it satisfies triangle inequality, and it really is a norm group. So that's how we'll have a concept of distance to define the same set W. And why am I doing this? Well, actually, we're going to look at maps from the circle to the circle, and we will get our result by showing that these are ergodic, and they're the maps that descend from maps from R to R, which completely not ergodic. They're not even measure preserving. So so it is important to work on the circle. I mean, I guess you could work on the reals and have everything being Z equivariant, but it'd be a massive. Why would you do that? When you can just work directly in the circle. Okay, so so we started out trying to talk about approximations of real numbers. We're now going to talk about approximations of points on the circle. And we were approximating reals by rationals. We're going to approximate points on the circles by points of finite order. So the points of finite order are rationals on the circle. And we have a norm, so we can talk about distances. So we can talk about approximations. Okay. And then this is not really any maths content here. This is just some language that'll be useful. So I've used this notation, the set of X such that X is in some set Sn. Sn was rationals with a given denominator, or rationals within a Sn was points X such that X minus Q is less than delta n, and the denominator of Q is equal to n when we were working on the reals. And on the circle, it's actually a little simpler. It's just points within a given distance of a point of order n. So that's actually just the limb soup, right, from say lattice theory. So it's just useful to be able to have a notation for that limb soup. Yeah, and then we have again, this is just language. So we'll talk about the delta thickening of a set. So we all know if you have a point, it's often useful to look at the ball around the point when you're in a metric space. And we're talking about approximations, we're talking about nearby points. So if you generalize the ball, instead of just having a singleton set, instead of having a point, you can look at the thickening of the ball. So we can do that. So if we give ourselves the language of limb soup and give ourselves a language of thickening, both of which make sense on the circle, then we can define the set that we're trying to study. We're trying to show it's either almost none of the circle, almost all of the circle. You can define this as it's a limb soup of the thickening of a sequence of sets, you thicken by your input sequence delta n, and then what do you thicken? Well, you thicken the points of order n. So O of x is the order of x, where x is an element of the circle. Okay, so this, so I haven't done any maths yet. All I've done is give some history and give a way to define the set that we care about in a new language. Okay, and so then how do we get there? So what background do we need? And when I was starting this, I had to have a look at MATLib and ask myself, was it plausible that I could formalize this result? Once I understood the proof. And you need elementary theories of like algebra, measure theory, topology, metric spaces, that other bits in between, order theory and so on. But that's pretty much what you want. And asking the most really of measure theory, so you need to have Lebesgue's density theorem. So I'll talk about that and remind you what that is, or tell you what it is, because you may not remember. You need to be able to talk about ergodic maps. That's probably the most important concept in the proof. You need an API for the circle. So I mentioned this, we happen not to have this when I started, so I built it and turned out to be useful. But we're already using it in other parts of the library now. And then you need to know stuff about non-trivial stuff about the circle. And the main non-trivial fact you need to know about the circle is that certain maps are ergodic. And then we also need this very clever lemma of castles, which we'll also get to. So that's the background. So I'll talk now, for the next, 15 or 20 minutes about the background, and then we'll assemble a proof of Gallagher's theorem, and hopefully I'll have some useful points about formalization to make along the way. Okay, so first of all, the Lebesgue's density theorem, that's first up on our menu of stuff to learn about. There's a big mouthful here that's a metric space with a measure and second countable. It's basically you've got a metric space, you've got a distance, and you've got a measure as well, and you've got a sigma algebra. And the important thing is that mu has to be doubling. So this roughly speaking, this says that if you have a ball of radius x and you double the radius, this is less than or equal to some constant times the ball of radius x or radius r. I haven't given you any quantifiers. It's for sufficiently small radii and for all x, and so there's a formal definition that don't need to worry about too much. Actually, I added the definition of that to MATLib as part of this work, so I could actually talk about the Lebesgue's density theorem. So okay, so that's the background. You've got a metric space, you've got a measurable metric, and it's doubling, so it's got this property. That's quite a lot of metrics, or rather, quite a lot of measures. It's not all measures, but it's a reasonably respectably wide class. All Riemannian manifolds, for example, their measures would be doubling. So what does the theorem state? Well, it says if you have some set S and you have some point in S, and you're going to look at the density of this point within the set S. So what's density? Well, you take a ball of a given radius and you look at the part that lies inside S as a ratio to the size of the whole ball. And then you take a limit as the radius goes to 0. And so you define a point has density 1 if, for this density, so this is the density here, if this goes to 1. And the theorem is that okay, so I just talked about a ball with a shrinking radius. You're actually allowed, the center of the balls is allowed to move around as well. And I need this fact, in fact. So I need the centers, but again, it's sort of just a detail, when we're speaking in Form AC, but the sequence of centers converging on some point, you've got a sequence of radii shrinking down, and that point has density 1 if for any such sequence the density tends to 1. So this is some theorem proved 100 odd years ago by Leibig, and the theorem is that almost all points in the set have density 1. So here's a formal statement. I couldn't quite get these both on the same slide, but I think it's kind of nice to look at this. Like somebody who's never seen lean before probably just thinks that's a mess. But even if you've only seen a bit of lean, it's not that hard to read, right? So, I've actually excluded the variables saying that we have, a measure space and a measure, so because that's sort of just noise for the theorem. But we have a set, and this, for almost all x delta mu restrict s. So that's for almost all points of s. So that maybe is a little bit of a mouthful, but quite a lot of it is recognizable. The measure of the set intersection with the closed ball centered at this point in the sequence with radius that, divided by the other one. Okay, this tends to 1. It's I think we have some distance to go in terms of getting even more readable, but anyway, for as some sort of a benchmark, that's how this compares formally at the moment. Okay, so that was one result that we needed. I was really happy that actually it followed more or less directly from a bunch of work that Sebastian Geisel had done, or Gutzel, I think I should pronounce that, for his enormous project on change of variables for integration. So I really I wrote to write a couple of 100 lines or something to just package up his work, but it was enormously helpful that he'd done that. And I said some of this already. So this condition about the limit of the ratio of the two balls, so we call that a point being density 1. And let's take an example. So if I take the closed interval 0, 1 in the reals, what are the points of density 1? It's meant to be almost all of these points. Well, it's the open interval. So if you take an actual endpoint, the points will have density 1/2, and if you take points outside, they'll have density 0. But if you take all points in the open interval, they'll all have density 1. So the theorem checks out there. Yeah, and the key assumption I mentioned already, you need this is doubling measure. Actually, the theorem, I wonder. Doubling measure is a pretty respectable class of measures, but you can actually have this for all measures if you make stronger assumptions on the space, like there's this Bezikovich spaces. We actually also have those theorems thanks to Sebastian. So I don't know of a common generalization that of the theorem that implies both. Maybe it exists, but anyway, we have both. Okay, so that was one thing that we needed. We needed Leibig's density theorem. I could have done some low powered version of this, because obviously Leibig just presumably proved this for the reals, and the circle is locally the reals, and could have been happy, but that would have been a bit of a pain. So the work here was just prove it for all doubling measures, show the circle has a doubling measure, and then I'll be able to use the density theorem on the circle. So that was one step. And then probably the biggest effort was developing our theory of ergodicity. So we didn't have this. We actually had almost everything else, which is great. So, what's an ergodic map? Well, it's a map which is measure preserving. So that means that, so if f is a map from x to y, and s is in here, and I guess f inverse of s is in here, then you want the measure of f inverse of s is the measure of s for all s. So that's, these are measure spaces. So this is the measure in x, this is the measure in x, and this is the measure in y, and this is the measure here and the measure here. So that's measure preserving maps. So why am I talking about measure preserving maps? Well, to be ergodic, first of all, you have to be measure preserving. But then ergodicness is a much more special property. It says that, well, if you're invariant, so if your pre-image does nothing, so your map from space to itself now, right? Measure preserving can go from anywhere to anywhere. But if you're mapped from space to itself and you're invariant under pre-image, well, then you must be almost empty or almost full. So that's just a definition. And it looks pretty relevant to Gallagher because the conclusion is of this form, but yeah, it's not like the theorem is a straightforward application of that, but it is indeed relevant. Okay, so this is maybe a bit of a better example. You know, I think the example of the density theorem's formal and informal versions was medium satisfaction level of how close they are. Not brilliant, not terrible. This is a bit more satisfactory here. So these are the definitions. I cut and paste these yesterday from MATLib source. I added these a few months ago. So I said, okay, a map is pre-ergodic with respect to a measure. It's prop, so it's a prop valued structure. There's no data. And it says, you know, if for all measurable sets, then this is our notation for almost equal in MATLib. You get used to it. So if you're invariant under pre-image, then you're almost equal to the empty set, or you're almost the whole set. So that's pre-ergodic, but ergodic is meant to be your measure preserving as well. So then I defined ergodic as for both measure preserving and pre-ergodic. Actually, this pattern of I actually don't need this structure because I could just have these are prop valued structures, so I could just have hypotheses of pre-erg. I could just have always carry around these two hypotheses. But I push for it, and I think it's nicer to actually have the concept of ergodicness. And you might say, why did I split this out at all? Well, there's quasi-ergodic maps are a thing. They're not nearly as well studied as ergodic maps, but they do exist, and some results are true for them. In fact, I proved results for quasi-ergodic where I could. So yeah, and they're the same as ergodic, except instead of measure preserving, you're quasi-measure preserving. So then, yeah, it's worth splitting out pre-ergodic. So it's like in MATLib, we have this really fine-grained hierarchy of properties that objects and maps and so on can have. Okay, so that's definition of ergodicity. Yeah, this is kind of a bit of a hint of like why should we be on the circle? So yeah, we're going to need to prove Gallagher's theorem, we're going to need the fact that on the circle, theta goes to n theta plus a constant. We're going to need to know that is ergodic for n is bigger than or equal to 2, a natural number. So in particular, it better be measure preserving. And like, if you've never seen that before, you might think, well, wait a minute, if I take r to r and I take x goes to nx, well, this can only be measure preserving if n is plus or minus 1, because otherwise, sets get bigger. But on the circle, actually, it works because if you have these two components. So this is some set. This is like the upper right quadrant of the circle, and if you take the pre-image under the doubling map, you do indeed get a smaller set, but you also get this other half of it, and together they have the right measure. So yeah, so there's some hope for this map to be ergodic, and although there'd be no hope on the reals again unless you work equivariantly. So I needed the definition. I needed the concept of ergodicity, so I added that, and then I needed to know that certain maps are ergodic, so I proved that. But before I know they're ergodic, I first need to know they're measure preserving. And I've given like a picture kind of that gives a sense of why it's true for the doubling map, or you can say even for the multiplication by n map. So you can kind of probably believe it now, but how do you prove this formally? It's dead easy, actually. If you just think about it, the measure on the circle is, we're just using the Haar measure. And Haar measures are unique. So it should just follow that if I, pull back this measure by the doubling function, I get another Haar measure. It has to be the same one. So yeah, and indeed, and this is just the statement of what I proved. I mean, I basically just took Floris van Doren's work about uniqueness of Haar measures and applied it to my specific situation. So just took a few of his lemmas and glued them together, and I got exactly what I wanted. So yeah, so G is the circle for me, but yeah, it's usual in MATLib, like that's, you need to be a commutative topological group, you need to be Hausdorff you need to take a hard measure, you need to be compact. So this is why the reals doesn't work. And then rootable by, this is just the multiplicative version of divisible. So the circle is divisible. You can take 1 over n times any element of the circle. And then in that case, the power map, or in the case of the circle, that's just the n. So g to the n multiplicatively is just n times g additively. And we have a 2 additive here. So yeah, we're saying, well, then we have a measure preserving map. Okay, so that's the statement of the measure preservingness that we want and the level of generality. As usual, when you add lots and lots of criteria, then the number of spaces satisfying them goes down. But anyway, it includes the circle and tori and so on. Okay, so that's fine. That's getting the maps to be measure preserving. But yeah, we needed more. So we also needed them to be ergodic. And actually, it was a bit of effort to prove that. So ultimately, I proved it via what I'm going to call this small rotation lemma. So here I've got the informal and formal statements side by side, because I'm hoping to convey a sense of where we are in terms of natural language versus formal language. So I'll call this lemma the small rotation lemma. So it says, if you've got a subset of the circle, and which is measurable, and I've got a sequence of finite order points. So ui, this might be 1 over n to the I, for example, or let's even make it more concrete. It might be 1 over 2 to the I. Then we have the ui plus s is almost equal to s, right? So that's, when I say ui plus s, that means you take this set s, and then you take the ith element of your sequence and you you just act on it pointwise. So that would mean you rotate it by some angle, which if I was using the sequence 1 over 2 to the I, it'd be like this tiny angle 1 over 2 to the I. So I've got a set, I've got a sequence. The conditions are that the set's invariant under rotations, if we think of it that way, by the angle defined in the sequence. And then the order of these points is finite, but tending to infinity. Then the set must be almost empty or almost the whole set. So this is certainly, it's different hypotheses to the ergodicity theorem, but it's the right conclusion. So it might not be so surprising. You can factor the proof of ergodicity through this. So this actually is pretty much the only property of the circle that you need for Gallagher's theorem. If one of the things that happens when you formalize work is you kind of really pair definitions and proofs back to their bare bones, and you see what you're really using. And this is the theorem about it's general definitions, but on a concrete space, the circle. So yeah, this is really what you need of the circle. And yeah, okay, so then the formal statement, what have we got? We've got a set. Actually, I think I said it's null measurable, so it's a slightly more general. I don't know why I proved this. Obviously, I just thought it might be useful. That means you can differ from a measurable set by a set of measure 0. So that's the concept of a non-measurable set. So all measurable sets are non-measurable. And then, okay, instead of a sequence, I've worked with any filter. That's more useful than you'd think, because you often start dealing with subsequences. So if you work with, it's often not so helpful to work with a really concrete type. You might think, oh no, sequences, that's how I think. Sequences are good. It's a map from the naturals into a space. But what if you need to pass to a subsequence, which I do actually in Gallagher's theorem? Then suddenly, you're indexed by a subtype of the nats, and this is a pain. If you just started out by proving your theorem for any type, maybe with a filter that, in this case, I just need to exclude this trivial filter case, then, if I need to pass to a subtype, then no problem. Okay, and then here's the condition. So ui plus s, so the set rotated, is equal to, so volume, that's the Haar measure on the circle. So this is almost equal to, with respect to the Haar measure on the circle. That's what this is saying to itself. And then the order of this is tending to at top. So it's tending to infinity. Then the set's almost empty or almost full. Okay, so that's the key property of the circle. And yeah, how do you get ergodicity from this? Well, this is maybe the nicest example of the informal, or rather of the formal statement looking quite attractive. ergodic. So this is the family of maps. If we know these are ergodic, we can kind of prove 90% of Gallaghers theorem. We actually still need a bit. We still need another application of the small rotation lemma, but we can. But these are certainly you can get almost all of Gallagher's theorem just from knowing the ergodicity of these. So how do you do it? Well, remember, ergodic means you're invariant under a map to yourself. So let's just consider the simpler case of there's no addition. It's just y goes to n times y. Well, then if your pre-image is yourself, then I can cook up a sequence whose pointwise action leaves a set invariance, and that's just 1 over n to the I. So for the doubling map, that's my sequence 1 over 2 to the I that I mentioned there. So, and that's because, if you apply the map enough times, well, the set's not changing because f inverse of s is s, but you kill that sequence eventually. So the small rotation lemma says, oh, okay, right. So if you have a set which is invariant under this map, let's say it's a doubling map or the tripling map or the quadrupling map, then it's got this rotational invariance property for lots of sequences that I can cook up, including this sequence 1 over n to the I. And so then it must be almost empty or almost full. Okay, so that's roughly how you can get ergodicity from the small rotation lemma. And then, yeah, just to comment on, so Gallaghers theorem uses this ergodicity for actually the sequence that you need is not just any n, but it's the primes. And then it has one more invocation of the small rotation lemma, where you use the sequence of primes themselves. Okay, so that's kind of a bit of a whirlwind tour of ergodicity and ergodicity of certain maps on the circle. But whatever you might take away, I think you can take away where, well, MathLib has pretty good measure theory library. We now can talk about ergodicity. We can prove non-trivial facts about ergodicity, like these maps of ergodicity of the circle. It is actually a bit of work to get these results. Okay, so maybe that's enough of a takeaway, and you're an expert. And then the last kind of technical thing before we get to the actual proof of Gallaghers theorem itself is this lemma of Castle's. So Castle's proved this, working in the same theory of Diophantine approximation shortly before Gallagher. In fact, this is, you can kind of, Gallagher had this really smart idea, but a lot of the good work, a lot of the groundwork is done by Castle's. So, and that includes this result. So it's quite a general result, actually. So he proves it, for, so what's involved in this result? There's 3 pieces of data. There's a space. So for Castle's, it's just the open interval and the reals. There's a measure where for Castle's, it's just the Lebesgue measure restricted to this interval. And then there's a sequence of spaces. Well, for Castle's, it's just a sequence of points. But actually, you can use subsets, and the theorem is still true. Just balls become thickenings. And I didn't generalize that, just for the sake of it. I actually needed the generalization from balls to thickenings. So, what is the lemma? It says, well, if I am in a measurable metric space and I have a sequence of subsets and I have a sequence of radii going to 0, then I can thicken up each subset by the corresponding radius, and I can take the limb sup of that. And Castle says, yeah, and guess what? If you do that, but you rescaled your metric by some constant, or equivalently, you replaced your radii all by some constant m, so this is just some constant, then up to sets of measure 0, like it does change your set, but up to sets of measure 0, it doesn't. So this limb sup of the thickening of a sequence of subsets by some radii going to 0, like it feels like a totally random thing, but that's exactly what occurs in Gallaghers theorem, which is not a totally random thing. It says that the object that you're concerning yourself with in Gallaghers theorem, part of the input is this set of radii. Well, you're allowed to rescale the radii by a constant, so it gives you a little bit of extra freedom, which is very useful. Okay, so that's Castle's lemma. Here's a formal statement of it. Again, just to give a sense of how close are formal and informal. Okay, so I put the variables in this time because I had room. So you have a metric space, a couple of weak conditions. It has a measure, and really the only important thing is it has to be it has to be locally finite, and it has to be a doubling measure again. Then this is the limb sup. B limb sup is just I wouldn't worry about that. I'm bounded by a predicate, but the limb sup of the thickening of this set by the radius scaled is almost equal with respect to the measure that you've got to the thickening without So okay, so it was actually a bit of work to add this. Again, the proof goes via the density theorem. So we previously used that to get the small rotation lemma, which we used for ergodicity. And then I used it again here for Castle's lemma. And yeah, Castle's lemma is like, it's obviously it's not super hard, but it's kind of clever, and it's not totally trivial because, you know, the density theorem itself is a bit of work. So yeah, so there's that. Yeah, the generalization, you know, like I said, you know, Castle's proved this for like very concrete setting that was perfectly suited to his needs, where you just had the open interval and you had the Lebesgue measure, and instead of a sequence of sets, you had a sequence of points. So why did I generalize it? I mean, partly because we like to generalize in MATLib, but and you know, there were no new ideas. Castle's proof 100% works in the general setting, but also partly because working like when in the informal application of Castle's lemma, the Gallagher uses Castle's lemma, and when both of them apply this lemma, actually their sequence, they do have a sequence of sets, not a sequence of points. So how are they able to apply their lemma that's for a sequence of points? Well, implicitly, I mean, you know, you wouldn't bother saying it informally, and they don't. The sequence of sets that they have are the rationals of, you know, given denominator, and they're just like say, well, you can actually enumerate. There's only finitely many rationals of each denominator, so you can just enumerate those and have a single sequence of points there, and then apply the lemma to that, and then observe that the conclusion you're drawing doesn't depend on the ordering that you put on the rationals to turn them from a sequence of sets into a sequence of points, and then get your conclusion. And informally, I think that's totally fine. But formally, it's really quite messy. So yeah, when I looked at this lemma and I was like, that's annoying. And then I realized, oh, it's just true for sets as well. And then I said, oh, but I just have to replace poles with thickenings. And, you know, then you sort of feel like you're closer to the way this should be. Okay, so anyway, so I didn't just generalize this for no reason. I really did need it. Okay, so I'm trying to, I started 5 minutes late, so I have 4 minutes left. So we're trying to get to the proof of Gallaghers theorem.
You can go on until you've finished. It's fine.
All right. I mean, I think I should be okay. I'm not expecting, like, I'm happy if somebody attending this talk just gets a sense of the sorts of ideas that you can now fluently discuss in MATLib. I'd be very happy if somebody, you know, learns new maths or takes away new details, but it's not necessary. So I kind of rush a bit. Anyway, yeah, so, okay. Keep mentioning Gallaghers theorem. We've already recast it as a limb sup of a thickening relative to your input data, which is just a sequence of the points of finite order on the circle. So this is the set which we're going to study. And there's just one final piece we need to know, and that's these sups, these sets, you know, the thickenings of the finite order points. These are not just random sets, right? You know, like, why can we say something like the limb sups of these sets? It's because these sets are not just any old sets. You know, they have certain properties. And what are the properties that we need? Well, it's how they interact with the group structure of the circle. That's what matters. So, you know, again, in an informal account, you don't really bother to, unless you're going to get new results somehow from this. You don't really bother to make these abstractions, but formally, you know, usually pays off, and I felt like it did here. So I said, okay, I will, you know, make a general definition for the thickening of the points of a given order by a given radius in a semi-normed group. And here it is. So this is the definition informally. And I sort of wondered if maybe geometric group theorists or people like that ever care about this, but I couldn't see that they do, to be honest. But anyway, here's the definition. So we have a semi-normed group. So that's the thing. We're taking the two additive of it. We have n. This is going to be the order. This is the radius, and we take the points of order n and we thicken them up. So this is all points that are within a distance delta of a point of order n. So on the circle, you know, this would be like, let's say I take n is 5. So where are the, you know, vertices of the pentagon, except for the origin. I don't have this one. This is excluded. And then, you know, you delta, you'd have some radius 2 delta here and some diameter, some radius delta, diameter 2 delta. So that would be this set for n equals 5, some small delta on the circle. So that's this definition. Okay, so, and then, you know, I said the reason that we can prove Gallaghers theorem is because these sets aren't just random sets. They interact with the group structure of the circle a bit, and that's a vague statement. Here's the precise statement. So, so I look through the Gallagher's theorem proof. What did I need? I need 4 properties. For the sake of time, I can slightly fly through this. I'll just say, so there's a mathlib lemma for each of these 4 properties. They're all elementary. The 4th one actually is a tiny bit of work, but it's all super elementary. It's like first year undergrad stuff. But like you might say, exercise 4 is a harder exercise. Okay, so you're talking about adding up several of these. You're talking about adding on an element to the group. You care about whether the order is co-prime. In this case, you need the square of the element to divide it. But yeah, so we need a little bit of API for points, for these sets which are within a distance delta of a point of order n. And then, okay, so in summary, just before we dive into the proof, which I'll fly through, we interpreted Gallagher's theorem now. It's a lim sup of points of approximate order on the circle using your input radius n, delta n. We use the density theorem to prove ergodicity. We also use it to prove Castle's lemma, which says that this is a lim sup of a thickening. These sets A, O, these are thickenings. So this is something, the exact shape of something that we have. And Castle says, as long as you only care up to sets of measure 0, you can scale your radii by some positive constant. And we have an API for points of approximate order in the circle. Okay, so that was it. That was like, 3,000 lines of MATLAB code to build this slide. And then there's the proof, or maybe it's like 3,400 lines, I'd say, yeah. And then the proof is just 100 lines more in MATLAB. So that's actually just the proof of Gallaghers theorem. So I'm technically out of time, but I'll use 2 minutes extra and I'll give you a sense. Okay, so how do you prove it, given everything on the previous slide? Well, we're looking at a lim sup of points of approximate order. I don't know how Gallagher thought of this, actually. It's very clever. He says, okay, well, for any prime, so P might be 2 or it might be 11 or whatever, for any prime, we're gonna divide up the set W that we care about into 3 pieces. I mean, these might intersect, but they certainly, their union is all of W. So P is just some random fixed prime. We won't worry about which one it is for now. So you divide up your lim sup into a lim sup where P doesn't divide n, where P divides n exactly once, and where P divides n twice or more. So these 3 conditions are, cover every number, and so the union of these 3 sets is W. Okay, so we can do this. What's the point? Well, the point is that the first one, the lim sup over numbers where your chosen prime P does not divide n. But that's because of this API for the points of approximate order, that's invariant under an ergodic map. Y goes to P times Y. The second one, where P divides exactly once, that's invariant under another ergodic map. So Y goes to P times Y plus a constant. That happens to be the constant, but anyway, doesn't matter what the constant is. And the third, sorry, when I say invariant up to sets of measure 0. And then the third one, actually, it is true, genuinely invariant. And yeah, you can just rotate this. Okay, so that's fine. Where does that get us? Well, right, so this is a proof of property A. I don't really, but you use the API for the points of approximate order, you use Castle's lemma, you get this. So yeah, so now, but this multiplying by P, that's an ergodic map. We proved that. So if you have a set, which is invariant in by multiplication by P, but this is an ergodic map, well then this set must be, for any prime, right? This must be almost empty or almost everything. So if it's almost everything, you're done because it's the subset of W. So W is almost everything and you're complete. So therefore you might as well assume it's almost empty. Same goes for the set B. You might as well assume that's almost empty because again, it's a subset of W, and if B is not almost empty, it has to be almost full because it's invariant under an ergodic map. So you might as well assume both A and B are almost empty for all primes. Well, that means, this is almost empty, this is almost empty. So W is almost equal to CP. And we only care about W up to sets of measure 0. So, yeah, so we have this. W is almost equal to CP, but CP is invariant under adding 1 over P, but that's true for all CP. So W is invariant under this. But then the small rotation lemma says, oh, hang on, in that case, you must be almost everything, almost nothing. Okay, so that's super, I haven't timed this perfectly, but that's a sense of how you get Gallagher's theorem. I recently wrote an informal account of Gallaghers theorem in LaTeX, for like a general mathematician, and it took me about 40 lines. It's 101 lines of lean. I feel like that's a pretty good ratio. And then, okay, maybe I'll stop now. I had some closing remarks, but they can kind of speak for themselves. Okay, so I'll leave it at that.